In chapter 7, we'll talk about a singular value decomposition. It's called SVD. And we start with singular values and singular vectors. Before I begin, we need to review the eigen decomposition. Eigen decomposition. We know that the eigenvector is just lambda times x, and then we call x vector our eigenvector. It's eigenvector. And the value lambda called eigenvalue. And so let's take an example. A is equal to 5, 4, 0, 3. And we get lambda 1 is equal to 5. And x1 is 1, 0. And then lambda 2 is equal to 3. And the corresponding eigenvector is 1 minus 2. So we can make eigenvector matrix like this, 1, 0, 1 minus 2. And we can write A is equal to x lambda x inverse, which is 1, 0, 1 minus 2, 5, 3, 0, 0, and I don't know x inverse here. But anyway, this is eigen decomposition. It's called eigen decomposition of matrix A. And well, for eigen decomposition, there is, a lot of assumption is there. A vector should be n by n. So only for a square matrix. So if you do eigen decomposition, and also we have to have enough eigenvectors. For n by n case, we have to have linearly independent eigenvectors, n eigenvectors. Otherwise, we cannot write in this way. So sometimes eigen decomposition is impossible, even for a square matrix. Sometimes eigen decomposition is impossible. But we want to talk about a singular value decomposition, SVD. So SVD there's a lot of difference. SVD is defined, any matrix is defined m by n. Any matrix, we can get singular value decomposition. So in that sense, eigen decomposition is totally different from singular value decomposition, because we can do singular value decomposition for any matrix. That is important. And also, we want to write, so I think we don't have enough space. SVD has the shape like A is equal to U times sigma V transpose, where U and V are orthogonal. I think I have to write here. U and V are orthogonal matrix. As you can see here, x1 vector and x2 vector, they're not orthogonal. In general, we cannot say x1 and x2 are orthogonal. Well, if a matrix is symmetric matrix, for example, here, A is a symmetric matrix, then we can have orthogonal eigenvectors. But in general, we cannot have that. But sometimes, there are two matrices, U and V. They're orthogonal here. U, V are orthogonal. But U and V, they're not inverse relationship, like X and X inverse is a totally different matrix, U and V. And so single value decomposition is possible for every matrix, and then U and V are different orthogonal matrix. And sometimes singular values, sometimes singular values and eigenvalues, they're the same. Real symmetric positive semi-definite matrix, singular values and singular value decomposition is exactly the same to eigen decomposition, but in other cases they're not equal. And also the singular values always non-negative, and that is also important. And this is an overview, and then we will keep going. For the same matrix A, 5, 4, 0, 3, we want to do singular value decomposition. And so in previous slide, we did eigen decomposition, but right now we want to find a singular value decomposition of matrix A. And we're going to talk about how to find that, but anyway, we assume that we find already the single value decomposition of A, and then you see here there are orthonormal vector here, 1, 1 and minus 1, 1, and you dot product and you can find that it's 0, so there are orthonormal vectors here, and then you can see another orthonormal vectors. I mean, they are orthonormal, and also they are orthonormal. I mean, the length is 1. Every vector has the length is equal to 1, and they are orthogonal each other. And in this case, we say we define a singular value. Singular values are called sigma 1, which is 3 square root 5, and sigma 2 is equal to square root of 5. So we have two singular value here, and then singular values here. And we have singular values. Singular values are scalars. And we have two sets of singular vectors. But, we have only one set of eigenvectors. But in singular value decomposition, in SVD, we have two sets, U and V. We have two sets of singular vectors. And so V is equal to 1 over square root 1, 1 minus 1, 1. And U is equal to 1 over square root of 10, 3, 1, and minus 1, 3. So SVD of A, singular value decomposition of A is equal to U sigma V transpose. Note that V transpose is equal to V inverse, and U transpose is U inverse, because U and V, they are orthogonal matrix, because their columns are orthonormal, and also their rows are orthonormal, but anyway. And if you write using a rank 1 matrix, we can write it as sigma 1, U1, V1 transpose, and plus sigma 2, U2, V2 transpose. And here, I forgot, here a sigma matrix, which is 3 square root of 5 and 0, 0, and square root of 5. So we have, you can see U here, and V and sigma, and they are all defined. And you see that matrix A is equal to this rank 1 matrix here, and plus rank 1 matrix. And you have to see that all the singular values are non-negative. So a singular value cannot be negative, but eigenvalue could be negative, as we know, but singular values always non-negative. We'll talk about the geometry of the SVD, and we know U are orthogonal matrix, and sigma is diagonal matrix, and V is also orthogonal matrix. Well, actually, V is orthogonal, but V transpose is equal to V inverse, and then if V is orthogonal matrix, and then V transpose is also orthogonal matrix, because orthogonal matrix, the definition is all the column vectors are orthonormal, but in that case, all the rows also are orthonormal. So V transpose is also orthogonal matrix, but anyway. And so A is the multiplication of 3 matrix, orthogonal, and then diagonal, and orthogonal. And all singular values should be non-negative. And you can try a singular value decomposition for every matrix. And that is important thing. Because sometimes eigendecomposition fails, but you can find SVD for any matrix. I mean, rectangular matrix is also possible. If A is 2 by 2 matrix, so this kind of singular value decomposition might be possible. Sigma 1, sigma 2, no, not sigma square, sigma 2. Sigma 2, 0, 0, cosine phi, sine phi minus sine phi, and the cosine phi. This is a rotation matrix, rotation by theta matrix. This is another rotation matrix. And this is a diagonal matrix, but we can think as a kind of a stretching matrix. Stretching. So we, if sigma 1 is equal to 2, we just make the length twice. And so we can think, we think A is just an operator, but what is doing? And we want to ask, it's just a number, A, B, C, D, but we don't know what is doing, what is A doing. But if you decomposition in this way, we can see that it's doing rotation first by phi, and then it's stretching the axis, and after that it's rotation again. So we can understand what is going on by multiplying A matrix. If you decompose that, we can interpret that, because orthogonal matrix usually rotation or just reflection and something like that. And so we can understand what is going on by multiplying matrix A. And S matrix, has a S matrix is a symmetric matrix, and if the symmetric matrix is positive definite or positive semi-definite, and SVD is the same as eigendecomposition. So this spectral decomposition. Sometimes we say spectral decomposition. We say this is a spectral decomposition. Spectral decomposition. Well, the reason is that the eigendecomposition is not for only for symmetric matrix, but we meet many symmetric matrix in any application, especially in quantum mechanics but there's a spectral theorem that eigendecomposition for a spectral theorem is always possible, and for a symmetric matrix we can have orthonormal eigenvectors, and that's why we can write it as this one. So we call eigendecomposition as spectral decomposition for a symmetric matrix. So anyway, so spectral decomposition is the same as a singular value decomposition for positive definite matrix. If a symmetric matrix is not positive semi-definite, in that case, we can have a negative eigenvalue. And in that case, what we need to do is just the singular vector can be used. Singular vector is just V1 could be just Q1, and U1 could be also Q1. But the only difference is that sigma 1 should be minus lambda 1. And then we can make it positive. So that is the important thing. So when you find a singular value decomposition, we have to know that a singular value values are always non-negative. If you write so if you find this kind of spectral decomposition and you find a negative eigenvalue, and somebody asked you need to find a single value decomposition, what you need to do is just to change the sign, and then you can find the singular value. So this is for a symmetric matrix. So symmetric positive definite matrix, you don't need to do anything. But if you have a singular symmetric matrix, and then if the symmetric matrix has a negative eigenvalue and the singular value is just a minus of that eigenvalue. This form, this singular value form, is only valid for real matrix A. For if you have a complex matrix, and it'll be U sigma V conjugate transpose, so that'll be all right. Or if you find any other textbook and that write A is equal to U sigma V Hermitian, or some textbook write U sigma V dagger. So that is Hermitian operation, conjugate transpose. Anyway, so the size of A is M by M, M by N, so is a general matrix, M by N, and U is M by M, and sigma is M by N, and the V transpose, which is N by N. So we will call that this is a full size form of the SVD. And if the rank of A rank of A, which is the independent number of independent columns in A, is equal to R, then we can have a reduced form of the SVD, which can be written as A is equal to U sigma V transpose, but this is M by N, but U is M by R, R by R, and this is R by N. So we can write it as sum of rank 1 matrices in the sigma 1, U1, V1 transpose, and so on, sigma R, U, R, V, R transpose. And yeah, this is a reduced form, and when we have, the rank is equal to R. So let's take an example. For example, example 2, we have a matrix A is equal to 1 to 2. And then singular value decomposition. We have the rank is only 1. We know that, because we have rank is only 1. And if we do singular value decomposition, and this is 1, and this is and we have sigma. 3 is a singular value for this matrix, and 1 over 3, 1 to 2. What is that? And this is U, and this is sigma, and this is V transpose. So this is a singular value decomposition for this simple matrix. So how to find U and V for this singular value decomposition? This is called SVD of A. And well, we can have a clue here. We calculate A transpose A, and we can see that this is U sigma V transpose and U sigma V transpose, and this is V sigma transpose, but it's just sigma because sigma is a diagonal matrix, and the U transpose U sigma V transpose. But we know that U transpose U is equal to I, because U is orthogonal matrix, and so we can cancel out here. So we can have V sigma, some kind of sigma square, but well, I think we have to write sigma transpose here, because in the full size form, sigma is not a diagonal matrix. I mean, it could be M by N. So for example, here this is in full size SVD. This is M by N, this is M by M, and M by N, and N by N. So that's why we cannot say sigma transpose is equal to sigma. So because their size could be different. So we say sigma transpose sigma V transpose. And also we can write AA transpose. We check what is it, and this is U sigma V transpose, and U sigma V transpose, and U sigma V transpose, V sigma transpose, U transpose. And we cancel out this one, because we know that V transpose is equal to V inverse. And we have U sigma transpose U transpose. So, and we know that, and U and V, they are orthogonal matrix. And also we know that A transpose A and AA transpose, they are symmetric. So we can see that this is just an, what is that? This is just the eigendecomposition of A transpose A. And we can write, what is that? This green one, this is eigendecomposition or spectral decomposition, I think that might be better, because A transpose A is symmetric matrix. So we can say spectral decomposition of A transpose A. So that's it. And so what we need to do to find U and V, what we need to do is we calculate first A transpose A. And then we find a spectral decomposition of A transpose A. Then we can find eigenvalue and eigenvector matrix. Eigenvector matrix of A transpose A will be V, and eigenvector matrix for AA transpose will be U. And so we can find, in that way, we can find U and V. And also we find the eigendecomposition of A transpose A, and then we can find the eigenvalue, and then square root of eigenvalue will be singular value. So just take this. So that's it, and we'll see an example for that. So this is the summary, and so the eigenvector matrix of A transpose A is equal to V, and eigenvector matrix of AA transpose is equal to U, and eigenvalue matrix of A transpose A is equal to sigma transpose sigma, and eigenvalue matrix of AA transpose will be sigma transpose. And so the steps for S3D is choose also normal vectors. First we find the V. And so we can find V1 and up to VR of A transpose A. So we can have V matrix here. And then after that, choose singular value, which will be square root of lambda k, where lambda k is an eigenvalue of A transpose A. And then after that, A VK will be a sigma UK. Well, this equation is from the single value, SVD, because you see that A is equal to U sigma V transpose, but V transpose is equal to V inverse. So we multiply V on both sides. What we have is AV is equal to U sigma. From this equation, we can have this relationship. So this just if you see just for the kth column of it, and that is this equation. That's why we have this equation. I think I should write a k here. And then from that, we can have uk vector is equal to 1 over sigma k and avk, and the k is equal to 1, 2, and so on up to r. And that is the procedure. Well, we have this information here. I mean, eigenvector matrix of AA transpose is equal to U, but well, in that case, we need to find AA transpose, and then we're going to do spectral decomposition again, and it takes a lot of time. So when you do singular value decomposition by your hand, not using any MATLAB or software, I think that is the best procedure, this one. And so you just find the V matrix first using A transpose A, and then you find singular value using eigenvalue of A transpose A, and then after that you find U using that equation. Not just don't go to AA transpose, so that's enough. You just consider A transpose A, and then you can find UK using this relationship, the final relationship. So in this way, you can find SVD using your hands. So we want to find the singular value decomposition of A matrix 5403, and first we calculate A transpose A, which is 25, 20, 20, 25. As you can see, this is a symmetric matrix, and the trace is just a sum of eigenvalue, and then or a sum of diagonal entries, which is 50, and the determinant of it is lambda 1 lambda 2, which is 25 square minus 20 square, which is 225. And so using this equation, because lambda 1 lambda 2 is equal to 225, and lambda 1 plus lambda 2 is 50, so we can find lambda 1, which is sigma 1 square, is 45, and eigenvector for A transpose A, which is 1 over square root 2, 1, 1. We normalized already. Lambda 2, which is sigma 2 square, is 5, and V2, which is eigenvector of A transpose A, and this is minus 1, 1. So right now we have a V matrix already, and because we know a V2 column here, and we know singular value here because we just square root of it, and then we can have singular value. And so we don't know only U matrix, and you can find it using this a V1, which is 5403 times 1 over square root 2, 1, 1, which is equal to sigma 1 U1. And similarly, we have 5403 and 1 over square root 2 and minus 1, 1. And it'll be sigma 2 U2. So we know sigma 1, and so we can find, so U1 vector here is 1 over square root 10, 1, 3, and U2, which is 1 over square root of 10 minus 3, 1. So we have a U matrix. So you just write A is U sigma V transpose, and you can write what is U, and we have 1 over square root 10, 1, 3, minus 3, 1, and sigma matrix will be square root of 45 and 0, 0 square root of 5. And finally, V transpose, and we have to write row direction because it should be V transpose. So we write 1, 1 here, and we write a minus 1, 1 here. So now we get a single value decomposition using our procedure. First calculate A transpose A. This is the first step. And then we calculate eigenvalue for this matrix and also eigenvector for this matrix. And finally, we use this equation. AV1 is equal to sigma 1 U1, and AV2 is equal to sigma 2 U2. So in that way, we can find SVD. We want to find the vector that maximizes the ratio here. So I mean, we have a system which is A. A is just m by n, a general matrix, and we have an input vector, x vector, and the output vector is ax. Is the output vector of the system, but we want to maximize the ratio of each vector. So it's a very natural question, and the answer is just the first singular vector, because when we I think I didn't mention that when we have singular value decomposition, like A is equal to U sigma V transpose, and we write singular value, which is a sigma 1 and a sigma r, but we have to order that. So we write in this way, sigma 2 and so on, and sigma r, of course, is greater than or equal to 0. So I think I had to mention that, but anyway, so a singular value should be ordered. So we can see that the sigma 1 is kind of a maximum constant for a stretching. You're stretching a vector, but some kind of stretching factor, I think the maximum stretching factor is sigma 1. So, but we want to find the x vector, the input, which will be the first singular vector of V. So the maximum value is of this one, of ax vector divided by x vector is sigma 1, the first singular value at the vector x is equal to v1. So this is why do we have to find singular value decomposition? And this is the answer, because in many times we want to find we want to solve this problem. We call this value, you see the square is there, but anyway, the ratio between output vector and input vector, we call it a Rayleigh quotient. So if you want to maximize a Rayleigh quotient, what is the answer? And you just find a singular value, first singular value. And that is the answer. Now we talk about section 7.2 is the image processing problem. By linear algebra. And we consider an image. Well, So we have an image, and this is image, and we think this is just m by n pixels there. So we have many pixels, and we know that A is U sigma V transpose, which is S3D, and this is sigma 1 U1 V1 transpose plus and so on, sigma R U R VR transpose. But we know that they are ordered, the singular values are ordered, so sigma 1 is greater than or equal to sigma 2, greater than or equal to, and so on, and sigma R greater than or equal to 0. So if we represent the image by this A matrix, we need a memory. How much memory we need? We need m by n space because it has m by n pixels. So we need m by n memory spaces. But we can approximate because sigma 1 is the largest one. So we can approximate A is almost equal to sigma 1 U1 V1 transpose. Maybe we can say that. To memorize, to memorize this value, what we need is just m plus n plus 1 space is necessary. The memory space. A memory space is necessary. So, which is normally a very small, smaller than m by n. So we can save a lot of memory, and we can save the image. If that approximation is not so good, then we can add more term, like we can add more sigma 2 U2 V2 transpose, and then it's just we can say it's just rank 2 approximation. In image, if we represent in this way, this is an exact way, and then we need rank R. So we need adding R terms, but we can approximate using just 1 or 2 terms. So in that way, we can. If we add just this term, and then what we need is just the memory space. Just what we need is 2 times n plus 1, and that's all. But normally it is also much less than m by n, so we can save a lot of space. So this is used in JPEG, the image compression, and we can use singular value decomposition to compressing. And this is the end of lecture for 7.1 and 7.2.